Hello, everyone. My name is Tina Burns, and I'm going to talk to you about a topic that is near and dear to each and every one of our hearts. Every one of us uses some sort of IoT device, whether it's our cell phones, a laptop, or a set of Bluetooth headphones. In fact, in 2021, there were over 13.8 billion activated IoT devices. And this number is expected to at least double within the next couple of years. And although advancements in technology are great, they do also present a unique problem that we need to address. If you look at this graph here, you'll see that the blue line represents the amount of allotted spectrum, and the orange line represents the new wireless traffic that is coming in. The amount of wireless traffic exceeded the allotted bandwidth or the allotted spectrum way before 2020. And then these numbers are continuing to increase daily. Now, this affects or has impact in several areas. So if a lot of people are trying to access the same spectrum, that usually leads to some sort of interference where you're getting undesired signals and you're having issues with your devices. In addition to that, in extreme circumstances, they could cause cell phone networks or cell phone towers or networks to actually crash. We saw this happen during 9/11 when a lot of people were simultaneously trying to access these cell phone networks. Moreover, this has or causes some privacy concerns for the military who would prefer having a dedicated bandwidth or spectrum for their applications. So what do we do about this issue? Well, one of the ways to mitigate it is through spectrum management. Now, we have said that the amount of allotted bandwidth does currently exceed, or the amount of traffic, wireless traffic does exceed the allotted bandwidth, but there are also times where certain spectrums or certain spaces are underutilized. So spectrum management is the process of taking these underutilized spaces and figuring out how to optimize them. Now, this involves three main steps. The first step is spectrum sensing. So determining what devices or what applications want access to a particular spectrum. And then second, making a decision on how you want to allocate that spectrum once you know what the devices are and what technology they're using. And then third, you are going to implement, or spectrum sharing will be implemented. And this involves dynamically allocating these applications to these underutilized spaces. So as we look at that, as we think about that, this is where our research comes in. One of the parts of spectrum sensing is device identification. And for device identification, you need, for a lot of these wireless devices in particular, some sort of automatic modulation recognition. Now, AMR is not a new area of research. That the military has actually been using it for decades. It's just that when we are considering a different approach to it. So when we look at AMR, it's relatively straightforward in terms of what's behind it. You take a bunch of modulation schemes, a bunch of device modulation schemes, and you try to classify them to output them to associate it to a particular set. Once you know what the modulation scheme is, you can couple that with layer 2 and 3 protocol information to tell you what device is transmitting or what device is trying to access your spectrum. Now, keep in mind that device identification has applications, or AMR has applications not only in spectrum management, but also for security purposes if you are trying to figure out whether or not a particular device should be accessing your network. So our project goals are to look at AMR from a little bit of a different perspective. And instead of just considering one main network, we're actually looking at 6 different classifiers. One of those classifiers actually being a match filter, which is not typically done, and then 5 additional neural networks. We want to examine the accuracy versus the SNR, as well as the latency and resource usage. And we want to take a look at the impact that different data sets have on this data. So when we look at our work in relation to other works, we'll see that there are some similarities and some differences. Similar to other works, we are getting very high accuracy in our results for the AMR classification. And we're also looking at this, or we're evaluating it with the accuracy versus the various SNR levels. But what sets us apart is, rather than just looking at one CNN network or making CNN the focal point of our networks, we're actually using 4 different networks besides the CNN network, and we're comparing that. This gives us a more robust view with how the CNN will compare with and how it holds up against these very different networks that it's being tested against. Moreover, we include the fully connected network in our results for AMR. Now, in the past, these networks have not typically been used because they have been thought to be unreliable or not produce as accurate results. And previously, it took a lot of time to train and test these networks. We also we're taking these networks, not just looking at accuracy, but we compare the timing of it. A lot of research doesn't necessarily compare the timing of, at least 5 networks across the 5 neural networks at the same time. So we're looking at that in the same environment to give a real view of how these networks are using the resources and both in terms of timing and their computational resources. Moreover, we are comparing these deep learning networks to match filters. Match filters are very common in sonar and radar, and they're very good at signal detection, even in the presence of the AWGN. But we wanted to look at that technology that's already currently being used and see how it would, how it compares to a deep learning network or deep learning networks in terms of classification for these modulation schemes. So now that we talked about how we're using different networks, let's talk about these networks themselves. Our classifiers, one of our classifiers, of course, is a CNN or convolutional neural network. And this has 17 layers and 4 output layers. For our fully connected network, it's a little bit more shallow with only 6 layers, and it again has 4 output classes. Our third network is a binary neural network. Now, the layers in this, or the neural network layers, are identical to the fully connected network. So they have the same 6 layers. What sets it apart is that we're algorithmically choosing how we want to classify this. For the first 2 networks, that is done with cross entropy, where it's just classifying them against those 4 networks. For the binary network, we actually label the data separately into 2 classes, 1 for the modulation scheme of interest and 0 otherwise. And then we take that and feed it into the networks, and we test each network separately. And then we take the results and use logic to determine whether or not we should classify that to a particular modulation scheme. Now, we thought that this would be beneficial because since it doesn't have the other 4 classes and it's 1 and 0, we were hoping that it would give higher accuracy results. Our fourth network is the autoencoder, which has gained some popularity because of its ability to handle unsupervised learning, which means you can actually, you don't have to label all of the data, but you can let the network itself pull out and classify the features and then output those, group them into a particular class. Our autoencoder has 10 neural network layers and 4 output classes. We use a long short-term memory network. We picked this network because of its ability to pick up on temporal patterns, and it's a recursive network and has been proven to be effective in some areas of research. And last but not least, we also consider a match filter classifier. Now, the match filter classifier, for that, we take a bank of match filters and we use that. We test it against the data with all of them being labeled for the modulation scheme that the filters are associated with. The highest output of that filter is considered the class, the modulation scheme that it belongs to. And then we use additional logic based on inference and Bayesian information to determine whether we want to keep it in that class or associate it with another class. What we found is that match filters are wonderful with detecting signals overall, but if there are multiple signals that have high power or are very densely populated, it makes it harder to determine what the threshold would be, and sometimes and often you get a lot of false positives. So what you'll see in our results is the match filter is actually not as effective because of these false positives. So with that being said, let's talk a little bit about the data that we're sending into these classifiers. We're using 4 modulation schemes, which are listed up here, and all of the information is output to binary files and with a 32-bit floating point values. We're using IQ information, and we selected that because we can get the IQ information relatively simply. It calls for a simpler radio chain, and it has lower latency because it's closer to the hardware. Also, we don't need to do feature extraction if we're just using the IQ data. Now, there is the option to look at frequency and higher level information, but that's something we want to consider for future work. With this data generation, we're actually looking at two types of data, right? The first one is synthetic data, and we use two platforms, GNU Radio and MATLAB, to generate this data. Now, both of these platforms are effective in radio generation. They have been used in a lot of research projects. Today, for this presentation, we're only going to focus on GNU Radio, but the MATLAB data is available in the paper as well. Now, what sets us apart from other research is that we take this GNU radio data and we transmit it over real radios, right? We use two USRP devices that are about 1 meter apart. We transmit that data over the air, and then we collect it from the receiver. And by doing that, we're seeing the direct impact that that the radios and multipath fading, noise, and other elements have on the data itself. So because we're doing a one-to-one comparing and we're taking the same data, we can really see how the classifiers respond to real-world environment issues. And that also is very useful information. So with that being said, we have the GNU radio data here, right? And what you'll see is that the CNN network does have the highest accuracy. It exceeds all the other ones typically in terms of its accuracy rating. But if we look at these other networks, particularly the fully connected network, the autoencoder, and the binary network, they're actually within 5% of the CNN classifier. Now, when we examine the LSTM and the match filter, we'll see that they lag behind. Now, the LSTM, as you see from the previous slides, it actually is a shallow network. And one of the reasons that it's so shallow is because we wanted to preserve time. As we will talk about in the next couple of slides, the LSTM network takes a massive amount of time to train and test. So we wanted to optimize both accuracy and resource usage. So it ends up being a little bit shallow. If we deepen the network, we could probably improve the accuracy. Now, the match filter is below average in terms of accuracy, and that is because in the presence of higher power signals, it is hard for it to classify, and we get a lot of false positives. Now, what is interesting to know here is that if you look at this, you'll see that all the networks pretty much reach their maximum accuracy around 0 dB. Now, when we take this GNU radio data and we transmit it over the air, we'll see that this accuracy has now shifted to the right-hand side, whereas before it was accurate at about almost 100% accuracy for the CNN at about 0 dB. Now that has changed and it's around 10 dB. You'll also notice that the gap between the CNN and the other networks is a lot wider. So now we talked about kind of why we chose such a shallow LSTM network. If you look here, this represents the timing for all of these networks, right? This LSTM network, why we make the LSTM network so shallow. The LSTM network takes a massive amount of time to train. So it takes over 10,000 seconds to train just for 244,000 samples. When we changed it to 2 million samples, it actually took 3 days, as opposed to the fully connected network, which took a couple hours. So we can see the difference in the timing. And it also takes a lot more time to test as well, as is indicated by this orange line. Now, when we look at the binary network, we see that it has a little bit more overhead time. The overhead time is everything outside of training and testing, such as labeling and other information. So when we compare the networks overall, we'll see that, yes, the convolutional network does have the highest accuracy, but it is at the expense of both the network timing and the resource usage. The number of parameters for the CNN is 32 times that of the fully connected network. And the timing, of course, is the timing for the FCNN is a fraction of what we need for both the LSTM and the CNN network. And although it's a little bit lower in accuracy, it's within 5 to 10% of that convolutional neural network. And this is why we believe that the FCNN is a network that should should be considered for automatic modulation recognition. I would like to take time to thank all those that helped me out on this project, and to acknowledge all those at WinLab and at Rutgers University. Also, if you want more information or you have questions, feel free to read the paper. And I thank you again for your time.